Very good morning, dear students. Welcome to my class. In my last class, I explained potential energy of a system of two charges in the absence of electric field and in an external electric field. So in this class, let us concentrate on one more concept, that is electric potential energy of a dipole placed in uniform electric field. So here also we are concentrating about electric potential energy of a dipole. We learned electric potential energy of a system of two charges. But here electric potential energy of a dipole which is placed in uniform electric field. And about the dipole, already we learnt in the first chapter itself. Dipole is nothing but a pair of equal and opposite charges separated by a small distance 2a. Let these lines represents uniform electric field, which is represented by E vector. A dipole is placed in uniform electric field minus Q plus Q. We know that this charge experiences a force which is in the direction of electric field. We shall call it as F plus Q. Whereas the minus Q also experience a force in the opposite direction to the uniform electric field. So we shall call it as F minus Q. It makes an angle theta. So here E is uniform electric field and dipole as dipole moment, which is from negative charge to positive charge. I'll write here P vector. Theta is angle between dipole moment, that is P vector, and electric field E vector. Look at this theta. Theta is the angle between dipole moment and uniform electric field. So when the dipole is placed in uniform electric field, what will happen? Already we learnt in the first chapter itself, when the dipole placed in uniform electric field, dipole experience torque. So torque acting on the dipole placed in uniform electric field is given by, we have an equation for the torque, that is tau is equal to PE sin theta. We shall mark it as equation number 1, which means when the dipole placed in uniform electric field, it experiences torque. What is torque? It is rotating force. How it is happening here? Look at this. This positive charge experiences a force which is in the direction of electric field, whereas this negative charge experiences force which is opposite to the direction of electric field. So what will happen? This dipole rotate in clockwise direction like this, which means the dipole which is placed in uniform electric field experience rotating force, that is given by PE sin theta. Now against this torque is rotating, which means the dipole is rotating in clockwise direction. So opposite to this direction, I need to rotate this dipole. So for that, what we required? Work done is required. Then what do you mean by electric potential energy of a dipole? It is the work done in rotating the dipole from zero energy position to any desired position in the uniform electric field. So in order to rotate this dipole in the uniform electric field, we required some amount of work done. That work done stored in the form of potential energy in the dipole. So let this dipole rotate through an angle d theta. Small work done in rotating a dipole through an angle d theta is given by. So what I am doing? Just I am rotating the dipole through a small angle d theta. To rotate a dipole through a small angle d theta, work done is needed. So let us calculate the work done. Small amount of work done dW. What is the general equation for work done? Force into displacement. So here the total force or resultant force acting on the dipole is 0 when it is placed in a uniform electric field. But in the place of force, what we have? Torque. Torque is nothing but what? Twisting force. So in the place of force, I will write torque. So force into displacement. What is the displacement? Through d theta. So d theta. Then dW is equal to, in the place of tau, we have a value. That is PE sin theta. PE sin theta into d theta. Equation number 2. So we calculated small amount of work done required to rotate a dipole through an angle d theta. Then what is the total amount of work done which we needed to rotate a dipole from theta 1 to theta 2? Total work done in rotating a dipole from theta 1 to theta 2. Total work done in order to rotate a dipole from theta 1 to theta 2 can be calculated by using integration. So total work done is capital letter W is equal to integration of from where to where? Theta 1 to theta 2. And we have already calculated small amount of work done. Then W is equal to theta 1 theta 2. What is dW? dW already we calculated, that is PE sin theta into d theta. Equation number 3. So we have to simplify this equation now. Now I need to simplify this equation. So here P is the electric dipole moment and E is the electric field. Both are constant. So we cannot able to integrate. So we need to take out. So W is equal to P into E, integration of theta 1 to theta 2. What is the remaining thing? Sin theta into d theta. Then W is equal to P into E. What is the integration of sin theta? Minus cos theta. What is the upper limit? Theta 2. Lower limit is theta 1. Then W is equal to PE. So I will take minus as a common. Then upper limit minus lower limit. So cos theta 2 minus cos theta 1. Then again I will simplify this equation. PE So minus into minus it is plus. So I can write cos theta 1 minus into plus minus cos theta 2. Okay. So W is equal to PE into cos theta 1 minus cos theta 2. Now, if initially the dipole is placed perpendicular to the direction of electric field, then theta 1 is equal to 90 degree. Then brought into some angle theta. So we shall call it as theta 2 is equal to theta. So for that I will write one diagram here. For example, just imagine this is the uniform electric field. So initially the dipole is placed like this. The dipole is placed like this. Positive charge, negative charge. This is the force F plus Q, F minus Q. So initially it is placed like this. So theta 1 is equal to 90 degree. And we rotate it through a distance theta. So like this I rotate it. Here positive charge F plus Q. This is theta 2 will be equal to some angle theta. So initially it is placed perpendicular to the direction of electric field, that is E, and it is rotated through an angle theta. So theta 2 is taken as theta. So here theta 1 90 degree, theta 2 is equal to theta. Then what will be the equation? W is equal to PE cos, what is theta 1? 90 degree minus cos, what is theta 2? That is theta. Cos 90 is 0. So W is equal to minus PE cos theta. This work done stored as potential energy in the dipole. So we shall write it as U is equal to minus PE cos theta. So this is the final expression. Electric potential energy of a dipole placed in uniform electric field. We have three cases. Let us check it out, the three cases. Case number 1. When theta is equal to 0 degree. Look at this. When theta is equal to 0 degree means the dipole moment and electric field both are parallel to each other, which means P parallel to E. So what will happen in this case? U is equal to minus PE cos 0 degree. Cos 0 is 1. That is U is equal to minus PE. Minimum potential energy. So in this position, or the dipole will be in stable equilibrium. Stable equilibrium. Case number 2. When theta is equal to 180 degree. So 180 degree means like this, which means the P dipole moment is anti-parallel to the direction of electric field. So P anti-parallel to electric field. By using this equation, U is equal to minus PE cos theta is 180 degree. So cos 180 is minus 1, minus into minus plus. So U is equal to P into E. So maximum potential energy. In this position, dipole will be in unstable equilibrium. So I will write here unstable equilibrium. Then case number 3 equal to 90 degree. 90 degree means the dipole moment is perpendicular to the direction of electric field. So P perpendicular to electric field. Using the equation U is equal to minus PE cos 90 degree. So cos 90 is 0. So U is equal to 0. So in this position, the potential energy of the dipole is 0. So these are the 3 cases. Case number 1, when theta is equal to 0 degree, then potential energy is minimum. When theta is equal to 180 degree, the potential energy is maximum. When theta is equal to 90 degree, the potential energy of a dipole is 0. Just now I explained electric potential energy of a dipole placed in uniform electric field. Then the next concept is electric potential due to a dipole. Electric potential due to an isolated point charge we learned. Now in this class we are going to understand electric potential due to a dipole. So here there are 2 derivations will come. The first one is electric potential at any point on the axial line due to a dipole. About the axial line, equatorial line, already we learned in the first chapter itself. Now the first derivation is electric potential at any point on the axial line due to a dipole. So I need to consider axial line. So minus Q, here we have plus Q, that is dipole. The distance between them is 2a. So it is on the based on axial line. So I'll take one axial line. So at this point I need to calculate electric potential at any point on the axial line. Look at this, this dotted line represents axial line. On the axial line, just I will mark one point. Either here also you can mark, here also you can mark, I marked here. So this is the midpoint of the dipole, we shall call it as O. So the point what I marked on the axial line, which is at a distance of R from the midpoint of the dipole. Small letter R. So the total distance between negative charge and the positive charge is 2a. Then from here to here it is a. Then from here to here it is a. So this is the actual diagram. To understand the electric potential at any point on the axial line due to a dipole. This is the dipole and this is the axial line. On the axial line I marked one point. In this point I need to calculate electric potential due to a dipole. The point which is at a distance r from the midpoint of the dipole, what will be the electric potential at that point we need to calculate. Now there is a potential at point P due to positive charge, whereas there is an electric potential at point P due to positive charge. So we shall give name as V minus Q for the electric potential due to negative charge, V plus Q electric potential due to positive charge. Electric potential due to minus Q. So we shall give name as V minus Q. So already we have an equation, general equation 1 over 4 pi epsilon naught Q by R. But what is the distance between the negative charge and the point P? From here to here it is R, from here to here it is A. So we shall write it as R plus A. Since it is due to negative charge, I will put negative sign here. But that's equation number 1. So V minus Q, that is electric potential at the point P due to negative charge. Similarly, electric potential due to plus Q. Electric potential due to plus Q, we shall give name as V plus Q. Due to positive charge, so positive sign 1 over 4 pi epsilon naught Q divided by, what is the distance between the positive charge and the point P? It is R minus A, because from here to here we require the distance. So R minus A. R minus A, marked as equation number 2. V minus Q, electric potential due to negative charge. V plus Q, electric potential due to positive charge. Then what is the resultant electric potential at this point due to dipole? So we need to calculate resultant electric potential or total electric potential. Resultant electric potential due to dipole. What are we supposed to do? We need to add. This V is equal to V minus Q plus V plus Q. So V is the resultant electric potential. Then V is equal to, what is V minus Q? We have minus 1 over 4 pi epsilon naught Q divided by R plus A. The same thing I'll write here, minus 1 over 4 pi epsilon naught Q divided by R plus A, plus, what is the V plus Q? 1 over 4 pi epsilon naught Q divided by R minus A. Look at this equation. Here we can take Q divided by 4 pi epsilon naught, Q divided by 4 pi epsilon naught as a common. I will take the same, Q divided by 4 pi epsilon naught as a common. Then I will open the bracket. First I will write this term, because this is a positive, no, I will write this one. So Q is already taken, the remaining is 1. 1 divided by R minus A, then minus 1 divided by R plus A. Just I have taken Q divided by 4 pi epsilon naught as a common. The remaining thing is 1 over R minus A minus 1 over R plus A. So minus sign is there. Then I need to simplify this. So I'll take the LCM. Q divided by 4 pi epsilon naught as a common. 1 into R plus A, that is R plus A, minus 1 into R minus A, that is R minus A. Let it be in the bracket. Divided by R minus A into R plus A can also be written as R square minus A square by using the relation A minus B into A plus B is equal to A square minus B square. So using this equation, I can write R minus A into R plus A as R square minus A square. Now I need to simplify this numerator. So here V is equal to Q divided by 4 pi epsilon naught R plus A into minus into plus, minus R minus into minus plus A divided by R square minus A square. So what will happen here? Plus R minus R gets cancelled. So what is the remaining thing here? A plus A, it is 2A. So V is equal to Q divided by 4 pi epsilon naught plus A plus A, that is 2A divided by R square minus A square. Now again I will do the simplification by taking Q q to this side, so it becomes 1 over 4 pi epsilon naught q into 2a divided by r square minus a square. But q into 2a is nothing but what? Electric dipole moment. So V is equal to 1 over 4 pi epsilon naught. So in the place of q into 2a, I can write p. So p divided by r square minus a square. Look at here, if the dipole is very short, r is very much greater than a, which means r square is very much greater than a square. If the dipole is short, it is r square very much greater than a square. So a square can be neglected. So we can neglect a square since it is a very small. So what will be the remaining equation? V is equal to 1 over 4 pi epsilon naught p divided by neglect a square. The remaining is r square. So this is the expression for electric potential at any point on the axial line due to a dipole. Which means it varies inversely to the distance, square of the distance. Next derivation, electric potential at any point on the equatorial line due to a dipole. Just now I explained electric potential at any point on the axial line due to a dipole. Now equatorial line due to a dipole. I will write a dipole minus q, the distance between them is 2a. The last derivation we consider axial line. Now I need to take equatorial line. Equatorial line is nothing but the line perpendicular to the axis of the dipole. So at this point I need to take this is the midpoint of the dipole, and the distance between the point P and the midpoint of the dipole is r. From here to here the distance is a, from here to here the distance is a. So for our convenience we shall give the name as A, here B. So we shall join this. There is a potential at P due to negative charge. There is a potential at point P due to positive charge. Now let me calculate both. So V minus Q. V minus Q is electric potential at the point P due to negative charge. So I will write the negative sign. 1 over 4 pi epsilon naught Q divided by the distance between them is not yet given. We shall write it as AP itself. So AP. What is AP? How can we calculate AP? By taking a triangle AOP. From triangle AOP or APO. So we need to apply Pythagoras theorem. If you apply the Pythagoras theorem, what you will get? AP square is equal to R square plus A square. Directly I am writing, instead of writing OP square plus OA square, directly I am writing R square plus A square. Why? Because OP square is nothing but R square. OA square is nothing but A square. So AP square is equal to R square plus A square. Then AP will be equal to root of R square plus A square. So in the place of AP, we shall write root of R square plus A square. Then V minus Q is equal to minus 1 over 4 pi epsilon naught Q divided by root of R square plus A square. Equation number 1. So equation number 1 gives electric potential at the point P due to negative charge. Similarly, V plus Q. What is the V plus Q? that is electric potential due to positive charge. Same equation, 1 over 4 pi epsilon naught, positive sign, Q divided by, what is the distance between the positive charge and the point P? We shall write it as BP. Again, by using triangle BPO, we need to apply Pythagoras theorem. What you will get? BP square is equal to R square plus A square. Same. BP square is equal to OP square plus OB square. So directly I am writing R square plus A square. So what you will get for BP? BP is equal to root of R square plus A square. So in the place of BP, we shall write Q divided by, in the place of BP, root of R square plus A square. We shall mark it as equation number 2. So equation number 2 gives electric potential at the point P due to positive charge. Again we need to calculate what is the resultant potential at this point due to dipole. So for this, V is equal to V minus Q plus V plus Q. Then V is equal to, what is the V minus Q? We have minus 1 over 4 pi epsilon naught Q divided by root of R square plus A square plus, what is V plus Q we have? That is, I will write here 1 over 4 pi epsilon naught Q divided by root of R square plus A square. So this is minus and this place both are equal in magnitude, both will cancel, then V is equal to 0. Electric potential at any point on the equatorial line due to a dipole will be equal to 0. So in this class we learned 3 derivations. The first one is electric potential energy of a dipole kept in uniform electric field. Then the next is electric potential due to a dipole. So under that we have 2 derivations. The first derivation we will learn electric potential at any point on the axial line due to a dipole. The next and third one is electric potential at any point on the equatorial line due to a dipole. The remaining things we will discuss in the next class. Thank you.